Today we will be discussing about the 100-page machine learning book in several parts. So the first thing is, what is machine learning? Machine learning is simply when you teach a machine to solve a problem or to complete a task normally which requires a human, but now can be done by the machine itself. So in machine learning you simply try to help the machine solve the problem by itself by giving it some data. On the basis of the data, the machine will create a statistical model based on the data, and the model is somehow able to solve the problem. So for example, there are four types of machine learning: supervised, semi-supervised, unsupervised, and reinforcement. In supervised learning, you have a data set which is a collection of labeled examples. So simply, you have a data set with, for example, house prices, right? So in this case, you have a x variable and a y variable. You can see here there is this x and y variable. Now in this case, this x variable are the variables you're going to use to be able to predict your y. So in our house price case, y will be your house price and x will be all the other variables which you will be using to predict the house price, like number of bathrooms, number of bedrooms, area in square feet, is it near a airport, is it near a station, railway station, number of which floor is it on, etc. Right? So that will be your x, and on the basis of these variables you will try to predict the house price, which is your y. Now you will see this small I over here, this little italic I. This is simply, it's a data set, right? So you won't have one example, you will have many examples. So obviously the first example will have every example will have an index. The first example will have index 0, then the second example will have index 1, third example will have index 2, and so on. So here I is for index. So if I equals 1, then it's x1 comma y1. If I equals 2, it's x2 comma y2. So y is our target or label, and x is known as the features. So each element x is called a feature vector, right? Now there you can have several x variables, you can have several features, right? In our case, as I said, we have number of bedrooms, number of bathrooms, etc. And that is why x is denoted as x to power of j, where this j is simply which feature is it, right? So for example, x1 in this case could be your number of bedrooms, x2 could be number of bathrooms, x3 could be area in square feet, and so on. So the feature, so there will be different features at different positions for j. Simply this is known as j. The power is known as j here. So the feature at every different position of j will always contain a different information. So x1 will be different, x2 will give you different information, x3 will give you different information, and then using all of these variables you will try to predict your y. Now the label, which is our y variable, can either be an element belonging to a, so it can either have a set number of answers, right? So like categorical, it could have 1, 2, like for example, when you roll a dice, so your target variable is what was the result. So then you have only 6 possibilities, right? 1 to 6. So it has a finite set of classes or possibilities, right? Or if you're checking for email spam detection, then it's spam and not spam, right? So either it is a finite set of classes, or it could be a real number which is continuous, right? It could be house price, so it could be anything, 24,400 if it's rent, or 50 lakh, 5 million, like there are too many possibilities, right? It will be 5 million, 5 million, and 1000. So there are many possibilities. So one where it has a finite set of classes, and one where it is a real number or it could also be a more complex structure. You could have a matrix in case of image detection, a graph in some cases, but mostly it is either a finite set of classes like in our categorical example where we talked about rolling a dice, or a real number like in the house price example. So the goal of a supervised learning algorithm is to use the data that we provided, create a model that will take our feature vector, which is all of our x variables, and use them to predict the y variable. Then there is unsupervised learning. In unsupervised learning, you have a collection of unlabeled examples. So there is no y variable, you are not trying to predict a certain variable. You just have an x, you just have some feature vectors. And your goal is to create a model which can either transform your x, which can take your x variable as an input and transform it, or into another value which can be used to solve a practical problem. So for example, in clustering, right, your model will have, like in clustering, simply what happens is it groups data of similar types into clusters. So for example, we are talking about height. People above 6 foot tall could be in a cluster known as cluster number 1. Then people of height between 5 feet to 6 feet will be in cluster 2. Then people below 5 feet will be in cluster 3. So this model will take our input data, which is the height, and return the ID, which is 1, 2 or 3, the number of the cluster for each feature in the data, right? So then there is dimensionality reduction, where simply you will take a lot of data, which is, for example, you have 20 x variables, and our model will output a new feature vector, like our x variables will be transformed and will now have fewer features than we gave it, right? Then there is outlier detection. So in outlier detection, simply you find out which records or variables are more different than the normal examples. So for example, which variable is way too far above the average? Someone 7 feet tall is out of the norm, right? Because usually you won't see someone 7 feet tall, so that is an outlier. Then there is semi-supervised learning. In semi-supervised learning, your data set will contain both labeled and unlabeled examples. The goal is same as the goal of supervised learning algorithm. You want to use your features and predict your target variable, but we are trying to use our unlabeled examples to compute a better model. Now you will think that this is probably not a smart thing to do, since you're adding more uncertainty. Your model has less answers and more questions in the data. But what happens is, for example, your model first was given a few labeled records, right? So 100 labeled records. So it was given the x and y features both. So it studied them. Then based on what it learned, it made predictions on the unlabeled data. So you gave it some labeled data, then you gave it a little unlabeled data, and then it gave you predictions for the unlabeled data. Now so the model will not only give predictions. Usually models also give you a confidence score, how confident they are that they have classified this record correctly. Now whichever data the model classified as 90% confident, you will label that data as whatever the model predicted. So if the model predicted that this person is if the model predicted this email is spam and it has a 90% confidence, even though you don't actually know the email is spam, you will allow the model to treat it as if it is a spam. So this way the model is able to practice over time and label by itself some of the data, and then it will retrain itself, and over time it will obviously improve. Then there is reinforcement learning. Reinforcement learning is simply when your model is present in an environment, like in the it is capable of actually perceiving the environment, right, as a vector. So simply when your model is actually present and has to perform some action, right? So for example, when you train a machine learning model to play chess, it is actually present in the game and it's supposed to execute some actions. Different actions bring different rewards, right? And so, and if you know, so the model will simply try to maximize the expected average reward, right? It will try to understand which move helped. So it will of course be, it will of course study on some data. It will know, it will watch some previous games of chess, and it will see which moves were more rewarding, and then based on that it will reward itself on a good move based on how it turned out, right? So reinforcement learning solves a kind of problem where you have to make decisions in the present, fast-paced decisions, right? So like game playing, robotics, logistics, etc. But we will not be focusing on reinforcement learning in this book. So how does supervised learning work? Supervised learning takes data in a collection. So there is an input and then there is an output, right? Input could be anything. For example, it could be messages, pictures, text, sensor measurements, anything. And outputs are usually numbers or labels. So your input could be whether your input could be the text or the email, and then your output could be whether it is spam or not spam. Or your input could be a picture and your output could be cat, dog or mouse. In some cases outputs are vectors. For example, if you created a object detecting model and it's supposed to detect a person, the 4 coordinates of the rectangle around the person in the picture will be the output, right? So they might have some other structures, but mostly they are vectors, categorical vectors, labels, and in some rare cases, you know, uh, sequences or something else. Let's say the problem. So let's say you're trying to solve a spam detection problem, right? So you gather the data for 10,000 email messages. Each has a label, spam or not spam. So you have the emails and whether they were spam or not spam. Now you have to convert each email message into a vector. So what is a vector? Let me make that clear first. A vector is a collection of ordered numbers, right? You know, so a vector is when you arrange the numbers. First of all, why are we even converting an email into a vector, into a series of numbers? Why are we even doing that? That is because our machine, computer, whatever you want to call it, model, cannot understand words. So it can only understand numbers. So what we are going to have to do is we're going to have to convert these messages which are made up of words into numbers. There are some methods of converting words to numbers. We will go into that later. But for now, we are for example using one known as bag of words. So it takes a dictionary of English words, and then for example, in a dictionary, the first entry will always be the letter A. You know, we say like is a word, right? So the first feature, which is will be equal to 1 if the email contains the word. Otherwise, the feature will be 0. So for example, if your email contains the word happy, then in this there will be like this columns of dictionary words, right, from A to Z, all the words, and then everyone else will have 0 except happy, which will have 1 because it was present in that email. Whichever word was not present will have 0, right? So you will repeat, so you will encode, you will give the numbers based on which words are present for every email in your collection. So this will give you 10,000 feature vectors, right? Because you will have like 10,000 you have 10,000 emails, and then each of, like, it will give you 10,000, you have 10,000 emails, and for each 10,000 emails you have 20,000 numerical dictionary words which will have numbers in them, and then a label. So now you have a machine data which the machine can understand, but the output is still in the form of human text, spam and not spam. So there is something known as label encoding which you can use to convert this into numbers. So 0 for not spam and 1 for spam. Now once you have converted the whole data into numbers, now we need to create a machine learning model which can study the data, identify patterns and make predictions based on it. The algorithm we will be using here is support vector machine. In this case we require that, so in this case we will want that our spam emails have a numeric value of 1 and our not spam emails have a value of -1. So you can go to your label encoder and re-encode your not spam from 0 to -1. So now you have a data set, a learning algorithm, and now you're ready to apply the learning algorithm on the data set. So you're ready to fit the learning algorithm to the data set. So what does SVM do? SVM will see every feature vector. So for example, we have what, 20,000 dictionary words, right, which we have converted into vectors, right, because they have number 0, 0, 0, 1, 0, 0, 0 based on which words were present in the email. So it will take every vector as a point, right, in a space. It will plot, right, it will plot this point in a on a plot, on a graph, and it will draw an imaginary hyperplane which will be a 19,999 dimensional line that will separate the example from the positive label, and so it will simply separate the positive labels from the negative labels, and this line will be known as a decision boundary. Now I know this may sound scary, so let me go back to someplace easy. So for example, we have in this case we have two variables, x2 and x1. x1 is our feature vector which we will be using to predict x2, and this red line is our decision boundary. This is because we have only two features, right, x1 and x2. We don't need a 19,999 dimensional hyperplane. Just a one dimensional line will be good enough. So for 2 dimensions we need a 1 dimensional line. If this would have been 3 dimensions, we would need a 2 dimensional square plane or something, and if it would have been 4 dimensional, we would need a 3 dimensional plane, and so on. So back to our current example, this red line is our decision boundary, right, and here we have, when this wx minus b you will see is written here, this is the equation for a line, y equals mx plus c, right, except in this case we are subtracting a bias because we will be using, because I will explain that, but for now let's just focus on the equation of a line, y equals mx plus c, but in our case it's minus, right. Here m has been converted to w and c is being known b, but b is simply the y-intercept, so it's y equals wx minus b, or in our case x2 equals wx minus b. Now all these blue dots over here are those emails which were spam, right, so which had the value 1. Remember when we label encoded our email labels, so all our spam emails are blue and have the value 1. So this the equation for this line, y equals mx plus y equals x2 equals wx minus b is 1, right. So all the variables above it or on it are 1, which means spam. Then there is this x2 equals wx minus b, which is equals to -1. So all the dots on this line or after this line are not spam, right. So anything on the one line, wx minus b equals 1 line, anything on it or before it is spam, and anything on the wx minus b equals -1 line or after it is not spam. And but this is just the lines we are using to make our predictions. There is another line here which is our main decision boundary, wx minus b equals 0. What is this? This is simply the main decision boundary. It is used. So how did we get this decision boundary? we get the decision boundary by maximizing the distance between this line and the nearby data points. So for example, this one blue dot, this other blue dot, and this orange dot, which are on these dotted lines, it will create a line which maximizes the distance between both. So for example, if this line would have been more towards the left, the distance between these two blue dots and this line would have decreased. So we create a line which is perfectly in the middle, where the distances between both categories is maximized. The reason we are doing this is because we want to be sure that we want our model to perform better. If we keep this line more towards the blue, more towards the spam emails, it will predict more emails as not spam, because it is taking very extreme cases as spam. But when we are keeping it at 0, anything that falls even slightly towards the spam will be spam. Anything which will fall slightly towards the not spam will be not spam. The distance between the dotted line and the red line is known as margin. So in our case, our y will be predicted by a model, and our model is known as function x. We are running a function on our x variable, and it is equals to w into x minus b. So that is why we have created the decision boundary, right, which has a main decision boundary and our two lines which are used for prediction. So the reason we are this margin, which is the space between the red line and the dotted line, is used for better generalization. This will the distance will ensure how our model will classify new examples in the future. And of course, we will want our machine to have minimum errors. So what we will want is our w and b values to be, x is already our input variable, so we cannot change our input variable, we cannot change our data. We can change how much these w and b variables, so that our line is changed, so that our line is such a line that it makes the least errors. So we want to optimize the values for w and b. So finding these optimum or these best values for the model, so for finding these best values, this whole process is called the statistic. So this whole process itself is the model, and the process of building the model is training. So this is how an SVM or support vector machine works. We will study this SVM in more detail in chapter 3. So why does the model work on new data? Why is it capable of predicting new data which it has not seen before accurately? The way it does that is by using this decision boundary. So if a new point falls, let's say here, it will know that this is a spam email, right, because it's falling with the rest of the spam emails, and it's falling on this dotted line, and it's falling on the other side of our red line. On this side there are the not spam emails, and on the left hand side of the line we have our spam emails. So it uses the previous records to try and find out which group is our new data point more similar to.